Okay, I think we can get going. So welcome everybody to this webinar. Today's topic is the analysis and localization of stereo-EEG data using BESA Research and the Depth Electrode Navigator Software DENS, which was produced by our partner company, Clinical Neuroscience Projects in the Netherlands. And yeah, actually guiding you through the analysis will be my very esteemed colleague, Dr. Mateusz Rosiniak, who is with me on the call. And I will now just give a little bit of an introduction. So what we want to do today is analyzing spikes, epileptic spikes in stereo-EEG data. We will also combine structural MRI and post-implantation CT data using the DENS software. And we will semi-automatically localize the stereo-EEG electrodes in DENS, and then we will highlight the sEEG analysis results in the DENS and also using the MIND software and show how to export that to DICOM. So there will also be time for questions, and also throughout this webinar, if you have any questions, please use the chat. Then I will be there to try and answer your questions, and we will also have a question and answer session at the end of this. The data set that we're going to work with today is a patient with epilepsy. We have a 24-hour combined sEEG and scalp electrode recording. So there was 9 sEEG electrodes in this patient. Each had about between 10 and 18 recorded contacts. So altogether, that sums up to 118 sEEG channels. And there was also 48 scalp electrodes. The data was sampled at 2 kilohertz. We downsampled it using BESA Research to 512 hertz for this analysis. There's also a preoperative MRI T1 scan and a postoperative CT scan available. This is a pipeline we're using for analysis of this type of data. So we're using the software BESA Research, BESA MRI, and then by our partner company, Clinical Neuroscience Projects, the MIND, which is a multi-modal imaging software, and the DENS software. So the first step in this analysis pipeline is to read the data to find events of interest in the sEEG data. Optionally, you can co-register the data with a T1 weighted MRI scan and then perform source imaging in BESA Research. In this case, this is possible because we also have the scalp electrodes available. Then in the MIND project, you can create a project to bring together the different modalities and visualize them together. In the DENS software, you can perform the segmentation of the stereo-EEG electrodes, and then you can bring it all together and integrate the data, visualize them together, get additional insights in your data, and do DICOM export for further exploration. And this is where I hand over to my colleague Mateusz. So thank you very much and have fun.
Hello, thank you, Harald, for introduction. And we have plenty to do today. So I will try to squeeze this in 1 hour. And let me just start. So we just jump into action. I hope you see my screen now. Is it working, Harald?
It is working, yes, thank you.
Yeah, wonderful. So I will just open the file and we will have a look on it. So just navigate to the place where I have my file and not this folder, and we have our CT data. So it looks like this. It's a bit messy, but in BESA Research, we can nicely navigate and we can look on the scalp channels simply by clicking this button here. We can look on the polygraphic channels and so on, but let's start slowly preparing the data sets. So the very first thing I will do is to perform co-registration. I already did the segmentation for MRI because it's a bit time consuming. And the cool thing is that we can start the co-registration and continue analyzing the data. And once the co-registration is done, it will be automatically loaded. So let's do it. And before doing that, I need to load the channel information, because with this data set, I have some electrodes. I'll just show you that they are not following 1010 standard, like CB channels here, but we want to use it. And luckily, BESA provides this electrode recognition. So we have a special channel configuration. You can go to the standard electrode folder, and we have this BESA MRI standard electrodes that has the extended data set, and it will automatically recognize these electrodes. So once we done it, it just recognizes the electrode naming, and we go to File and MRI co-registration. We just start the co-registration. The MRI will be brought to you automatically. I will generate FEM, so finite element model for better source localization. I already said that I prepared the project for you. That's basically a few clicks away. We have it already co-registered, and we now need to wait for the FEM computation. I will leave it in the background, so it will be computing. And when it's done, we will be having the proper data. But now let's look on the scalp EEG and get rid of the problematic channels. So we have this very noisy channels. I will just interpolate them. Those that are the most noisy one, because they will make a lot of problems for us later. So now we have a more or less, let's say, good data set with P8. I'm not sure. Let's see how it will look like after the filtration. When we apply the filtration, we need to apply some filtration. Let's say we'll go up to 40 Hertz, and we apply the notch filter on this data set. We start from the 3 Hertz. And yes, this P8 looks good. But let's do the final verification. The final verification is to check the channel distribution on the most known thing, like an eye blink. So let's look how it looks like. This is maybe not the best eye blink, actually. So let me check another eye blink. And then when we check this eye blink, you can see something very intriguing here. We have a nice frontal topography, but here on the channel P8, we have something not typical for the eye blink. Let's see if that repeats. Yeah, there's still something fishy happening with this P8. Let me double check here. Yeah. So actually P8 is again the wrong channel. This is very important for you to know that it's worth checking, because later all our results will be spoiled by this. So I will interpolate P8, and now we can close the mapping and restart the mapping to see. Yeah, now it looks fully correct. So once we done this, we can go and find we can change the montage to original average reference, and we can also switch to polygraphic channels. You see that there is a lot, but in this case, we can just trim our viewing to selected channel group. So look on the first quarter, we have these AR channels, we have this another group, and we have later the channels that are not used. The C will get rid of this later, but let's focus on the first quarter group. And here we need to find a spike. You will see that this AR channels get stabilized later. So it's everything fine. We don't need to do anything. However, we have a 23-hour recording and a lot of channels. So processing this data will take quite a while. And if you are in such a case, you have a long recording and you know that you can trim your results to the given time span, we can do it to not perform the search over the entire data set. I will show you how to do it. We go to the event log, and in our case, we have the start marker here somewhere later. Let me look for it. Where is the start? Here, begin. So I will just put a marker here, And for our webinar, I will just go make it very short. So I will go to position in time at 1 p.m. Just put the marker here. And now we just go to event. We need to, I have already marked spike for you, so we don't need to hunt for it. We just need to go to the first spike I know. Here we have a spike. I will just mark at the peak, do the default block, go to select the channels where I would like to look for the spike. So there's 3 channels. And then I will just perform the spike search. So I use our current filters because we know that it was very noisy at the higher frequencies. We want to use our selected channels. Let's go with the default block, and we would like to see the search results. And in the search range, we would like to perform the search between markers we just put to trim for this very narrow window to make it short time. And we just wait for a second that will go through data and look for the spikes. We can see how it works. It finds already a few spikes. Halfway there. We found the markers. We found some spikes. By the way, let's see BESA MRI, how we are standing there. It's finished. So when I press finish, it will just allow for saving. We can now close BESA MRI. And then if we go to file, MRI co-registration BESA MRI, we will see that we have this individual film already loaded and everything works like charm. And now when we go to view, selected view, unfortunately, it was for the moment it switched off, but we can always back to this view. And what we can do right now, we can just scroll through the data and remove the events that we don't like. I don't see actually any events that I don't like. All of them looks quite nice, but just for the teaching purposes, I will just show you, let's say I don't want to have this event. So I just mark it and press delete on my keyboard, and that will just remove the event from the list. But to make it better, I will actually load the search results over the whole file. It took quite a long time, let's say roughly 25 or up to half an hour to search of the entire file. So I will just load the search results that I did for you before. And now we would like to average this spikes. So we go to first, we need to convert the spike, so the search results. I'll just show you one of the spikes here. So here is our spike, and it's marked as a pattern. It's not yet trigger. So we need to, for the purpose of averaging, we need to convert this finding to a trigger. So kind of accept it for the processing. And it's very easy. We go to ERP edit triggers, we select a tag, and we assign a code. And that's basically all we need to do. So we have it assigned, and then we go to ERP module for the averaging purposes. We just assign this code to condition. We define the epoch. I will do it from -200 to 250. And baseline will be -250 to -150. So we know that we are before the spike. We can perform the final artifact check. If there is any residual artifact, I will use the same filters just for scanning. It took quite a while, so we will see also how many events we have there. Because I would like to also show you how good and accurate is the distributed source localization based on EEG. So we see that we have Some events that were based on EEG quite noisy. We can see it here, that there is a bit of noise here. We can automatically reject it. And then we go for the averaging, just one button click, and we'll have our average spike. I will just save it. We need to apply the same filtration. And now we can look on the scalp data, and we see that there is also a very nice spike here. So let's try. T10 probably need to be interpolated as well. And then let's look at how it looks on the what we can do with the source localization. With this, I will just trim the results. Just shortly mark the interval. Let's see where the spike localize. We can see the atlas, and it is hippocampus. So this is exactly where we suspect to have it. This is a spoiler alert. We can also do the Clara for it to see the distributed sources as well, where it will be located. As you see, it's also already using the individual anatomy, and everything is prepared. We have a dipole, we have a discrete source, and we can now review these results. We can see how it looks like in the space of in both cases, we are very close into hippocampus, so this is a very good. But we are focusing on the stereo-EEG. That's the data that we have. And if we want to combine it, we can use Mind and DENS software. And now we are going to export the results we have here to Mind and then go to DENS. So to do that, we have a shortcut that you go to Run Batch option in Fit, and you can select Mind. It will just export the data. We can name it as the distributed solution. I will name as Clara. And it will create and open the Mind for us in a second. Hopefully it will work. Yes. So we have automatically filled out the subject from the MRI project. We can just press OK. So all the data will be automatically loaded. So the dipole and Clara will be loaded here. We only need to add CT to the data set. I'll do it in a second. By the way, for unknown reason, both programs, BESA MRI and Mind, when I do it over the Teams, are much slower than usual. It's somehow the Teams, not Teams, but the Zoom effect that will slow down the processing. Anyway, here I just need to add the data and just indicate what type of the data it is, if needed. And I just need to add the CT data to the project, which I have in my folder. So automatically load it. Okay. So we load it. It will load everything. The only thing we need to do is to do a bit of preparation of the project. We have a warning that there is some data sets that they are not overlapping, which is basically CT because it's registered in a different session and different machine, but we will solve this problem in a second. Okay, so we have loaded this one. Actually, I loaded by accident. We don't need this level volume. I will just easily remove it from the data set. Okay, I can just easily remove it. So we have our dipole. We have our Clara that is shadowing everything because it has 0 values. We can just see it here with the Clara results here with the color. We can change the color to hot map. I will just play with it so we can just trim it a bit. Nicely shown. Okay, and I told you that this CT data is not matching with the other data sets. So probably if we go out, we will be able to see that here is our MRI and here is our CT, and we need the aligned volumes. So for this, we have a button here that will perform the alignment. It automatically selects the volume that is not aligned. It selects the MRI, and we just need to press OK and wait for yet another 1 or 2 minutes. Or let's see how it goes with the zoom in the background. But that's what it's done. The next step would be to remove the skull, which we also have the algorithm for this. It's called brain extraction. In a second, I will be running. We need to do it on the MRI and CT for the reason to mark the electrodes. And marking the electrodes and segmentation of the electrodes can be done in most cases automatically. In that particular case, our CT data is not the highest quality. You will see it's full of artifacts, so the automatic assignment does not work in some cases, but also we can use the computer-aided approach to mark the electrodes, and this is fairly easy and fast procedure. I will show you how to do it, and then we can prepare it. Okay, so we have this volume alignment almost done. Okay, it's aligned. So now we can just simply, to see how it works, we can just play with the opacity. We can change the color scale, let's say, to green. So now we can see how it's nicely overlap between the both images. And now we need to run the brain extraction on both CT and MRI. So I will start with MRI. It's a bit of waiting, but still better to wait than do it manually. As you see, it's nicely extracted the brain. And now we need to perform the same thing on the CT. And then we are ready to go for electrode mapping. By the way, if you go directly to DENS, so you skip the whole mind part when you can do the integration with multimodal imaging, and then you are guided directly how to do it, and the software automatically click the buttons for you. So it's a bit easier, but you will lose the option to load the results from the multimodality. or you can actually load it later manually as well. This is also an option, but it's not that automatized, so I prefer doing this way. So now we have the extracted data, and then we just need to verify all these data sets that they are correct, registered. So this is all we need to do. So all of this is registered and working. And by the way, why we do it this direction is that the Clara image and the dipoles, they don't have the brain space. So if they don't have a brain space and the skull and so on, they cannot be registered. So we need to use this MRI T1 ACPC from BESA MRI as the core project, and everything is co-registered to it, because then we can be sure that the Clara and the dipoles are in a proper position in the space of MRI. Okay, so we are done here. The last thing we need to do is to export the dipole. We just need to mark this as the region. So we need to save the project and just jump to exploration, because in exploration we can create a region around the dipole so we can see it in DENS. Almost there. So we have our dipole here. It's still loading a bit. Slowly getting there. And then it's surprising how Zoom slows down the entire PC. Quite extensive, even though I have a quite powerful PC, Zoom still kind of blocked it a bit. Okay, so I can now add custom region. I'll just make a small dipole around a small region. I will just make it with the different color, let's say gold. And yeah, we are ready to go. We can rename it. So this is our dipole from EEG. And we can save the project. And then we can just simply go to the Depth Electrode Navigator. It will open another program here. Where it is. And the case is that when you configure the installation, you need to be sure that both programs has the same folder of database, because when it's done and you click to database, you can have the access to the project that we just verified and we created. So when we press open, it will open the project that we just created. So you seamlessly go from one project to another, and one options to do from another. And we already see our region, we see our Clara results, and we only need to do is to perform the depth electrodes. It will ask which volume it would like to use, so it automatically select everything, and we just press OK, and it will try to detect electrodes, but unfortunately, I will show you in a second that in this noisy CT data, it didn't work. So as usual, in our approach, we recommend for you that you really should care about the data quality, both EEG, CT, and MRI, because it makes your life much easier later. But if not, we can still work with it and fix it. So I will just go, I'm actually preferring to do it on the original CT. So yeah, what we need to do is to just mark the electrodes and check the electrodes. So let's start step by step. We have electrode 1. That is actually not so bad, but it's a bit too short. You see that there is an electrode tip a bit later, so we can edit it. We just press this cogwheel button, and just basically for this one particular electrode, we need to go to the tip of it and just select the tip. And then we need to check the up part of it, if this is correct. Let me just double check with it where it's the, yeah, it's, we don't need to be on a very tip. It will automatically select. I like to just select the bright spot. And then we know that for this particular electrodes, the contact spacing was 1.3 centimeters. And then we need to figure out what is the name of this electrode. And this is, let's say, a bit tricky part because we need to use the information that we get from hospital. And here, what we have, what electrode we have here, this is the electrode that goes from the frontal lobe to the very deep structures. So let's see what electrodes we have that goes from the frontal. So we have this 2 electrodes that goes through frontal, but one ends in the insula and second ends in orbitofrontal, so a bit lower. So that will be a longer one. So we have this 2 electrodes, as you see, one here, going through the frontal, but this one ends very deep. So that will be the one that ends in the orbitofrontal. And later, because in our case in BESA Research, these electrodes are, where's my data set? You will see that the polygraphic channels, so the scalp channel, the stereo-EEG was recognized as polygraphic. We need to name these electrodes as poly. So pole, and the name of this electrode was OFCR. You will see in a second why we do it this way. So we have the first electrode marked, checked. So for me, it's actually, I like to do it this way, that I just put my check mark here that this was done. Okay, so yeah, then we talk about the second frontal electrode. That was somewhere here. Yes, this was this one. Which one is the close to this one? Yes, so we have this E6 and E2. They're more or less the same, so I will just delete E6. We don't need it at the moment. We just go for E2, and we need to fix the E2. So E2 phase is somewhere here. We know that the contract will be 1.3, and we just need to find the tip. So I'm just scrolling around the data. Oh, and it might be that I actually not correctly said the naming. I told you that this is a tricky part, especially for me. So we know that it was the frontal. We have here the frontal. So that will be actually, so this one will be the shorter one. So that will be the ER. Because this is the shorter one, and E2 is the longer one. So and both cases it was 0.3, and both has the 18 contacts. So we just set the number of contacts to 18. Okay. And then let's continue. Electrode E3. So E3 goes like this. It's actually properly recognized. The only thing we need to do for E3 is to put the name and set the number of contacts. So the distance is 1.3. And this is the one that it's easy because it goes back. So this one, these two we have. Now we need to assign, and this is going, we have only one that going from the parietal region. So this one. So this is the CR. CR. And it has the 12 contacts. And there we go. So now we have a tricky part because we mark already all the electrodes that were done. This is not correct. It was from the EEG electrode artifact. This one is correct, but we will mark it anyway manually. Or we can just remove it to make it easier. Because the temporal are more tricky. So let's start with the left side, because on the left side, we have some electrodes here. And my approach is that I prefer to go in the Z direction from bottom to top and look on the lowest contact on this. So the lowest one will be, in that case, the AL electrode. So I'm going from I will just need to put the electrode and just go from the bottom, find the lowest one. So the lowest one is here. I have a contact and I will just set the base of it. And now just go a bit up. So I found the stick, set the base, set the number, set the distance, and AL has the 12 contacts. So easier like this, just rename it to pull AL. Then we go to the, let's say, second electrode. We put another one. We go up. We just set the contact. Here we go. Set base. And just a bit up to find the further part of the electrode. Base. Distance 1.3. And again, 12 contacts as far as I remember. You can check. Yes. And this was the name HL. Done. Okay, so far so good. We have already done quite a lot. And now the most difficult part is the right-hand side, because here we have a lot of electrodes, which is a bit tricky to find. But with my approach, going from the most bottom to top should not be so difficult. I will just, for the moment, I will just disable the custom regions and Clara, so it will be not shadowing our electrodes. We can easily do it. So we go, the most bottom electrode. We have the pin, I will just add the electrode and go here, and we have the electrode pin tip, and then we go a bit up from here, so to track the final part of the electrode. And the lowest one was we look on the Z coordinate here. Yeah, this is the ECR. So, and ECR has the 10 contacts, so we name it ECR. We put the 10 contacts. We keep an eye on the number of, so on the spacing. So we are done. We will add a new electrode. And again, we go up from the bottom to the up. So as you see, it's a bit of tedious job. And here we have to be careful because we can spot one electrode that is deeper than the another one. So be sure not to mix it up. So you see that this electrode is actually the more deeper one is this one. So here we set up the, let me just make sure that we are on the proper spot. Yes. So we set the tip, and now we go a bit up to go to upper part, base, and this was the Z -8. This is HR electrode, and HR has the 12 contacts. I think all of them now have the 12 contacts. And again, we repeat the procedure for the missing 2 one. It's, as you see, it's not so difficult, but we have to be careful not to mess it up. Okay, this one electrode actually goes a bit down, so we need to scroll a bit down. Here we go. And then again, spacing and number of electrodes. And that was we set ER, we set ECR, we set HR, and now we have this PHCR, if I'm not mistaken. Yes, so that will be. And the last one should be, we can just put it here and we can just scroll and try to find the one that it's going right here. We almost found it. So let me just go with you to mark the pinpoint on it. Let's make sure that we are in the proper spot. So this is the tip. And again, we just need to go a bit higher to find the stick base. And again, 12 contacts and spacing. And we are, and the name of it was AR as far as I remember. The missing one. Oh, we are still missing one. Do we have the IR? Did I make any IR? Yes, I did. So I forgot just to check that we did it. So this is the AR. Okay, so with this, we have our electrodes. We can back to the, we are done with the redefinition of the electrodes. We have all electrodes marked. We can forget about the CT now. We can load our Clara and the image, and already nicely see that our dipole and Clara results are quite close to the results, but we can still load. We would like to see the actual data of EEG or sEEG on the data set. We are almost there to do that. But as you know, in the data set, we have much more. We have a scalp data. We have some electrodes, as you remember, that they were missing. So when you look on this, we have the CR that were not used. So we can just need shortly to, I have a problem. I have, okay. So I need to remove for a second the channels that are not the one that I need. So basically here is I go to the montage editor. I have my ECR channels and so on, all my stereo-EEG up to here. And here, all these channels are leftovers that I just don't need. So I just mark them with pressing my shift button. and press the delete key. So now I only keep the stereo-EEG channels and press this button to apply the montage. I can press no to use just a temporary montage with the filters I already defined. I just would like to export this to EDF using current montage and current filter. I will name it sEEG. Oops. Okay, why this didn't work? Let me just redo the thing. So I will just save it as the montage then, just for. Okay. And I can load this data here by pressing the plus button. We go to place where I exported this data. It's nicely loaded. And then I put my cursor here. We zoom in. And then with the color, we can nicely see how good our distributed solution and discrete solution is with what we found out from the stereo-EEG. We can change the color maybe to something more informative, like flow light. We can even do some cool thing on the visualization part. So we can go and render the skin. And now we can render the cortex. We change opacity. So Claro, you can render the results. And this is very nice result, I would say, to show how it looks like. Let me just organize the view for you. So now we can see how it works nicely. And yeah, that is kind of a thing. However, we can do one more thing that is extra in BESA Research. When you go back to this data set, we can check the relationship between the data sets, between the electrodes. So now we see that this HR3 has the highest amplitude. What we can do, we can press L on the keyboard to check the correlation. Let me just show you. This is a small numbers, but maybe I can just trim it up to this small electrode subset. So first quarter or first half. I will just press L once again. And then you can see that the highest amplitude is automatically, we don't even need to select it. Select the highest amplitude, it was HR3, where it has this 100%. And then with the red colors, we have the related channels marked. And then you can see that the channel actually number one has the lag. So it shows 5 milliseconds beforehand. So it might be that this is the onset. And that's the most important one, even though it has the lowest signal, a lower signal than the others. And this we can utilize as well. Yep. So the final part would be to export the DICOM. So to export the DICOM, it's super easy. We just go back here. We go to the custom regions, and eventually for us, we now know that the region can be mixture of this, and we would like to be based on the electrode. So we just put our marker here. We put the custom region. We just we add the plus button. If that works. For unknown reason, I cannot. You just verify all the data sets and go again to the custom regions. Go here. I think that this custom regions I can only load in the Mind software. This plus is not working here. So we will need to go back to Mind. And the cool thing is that in the Mind, we can also, when we save this project, we can open it again in Mind. So we close the project, or actually load project. It will reload the project, but now with the electrodes. You can see that it's nicely loaded up. So we remember that it was around here, our main region. So we go to custom regions, and now we can add the new dipole. We can make it a bit like this. We can make it green. We can rename it as this from sEEG. And with this, we can now export this to DICOM. Or actually, I should click regions to DICOM. Sorry for that. So we can select both. Now we select the source. So I will select the MRI. And now we need to select where to save it. So I will create a new folder with demo. I will select this as a folder, and that's exporting. And now we, for example, can go to any other folder like ITK Snap. and we will open the one that we just exported. So it was here in the DENS demo. We have this, I think we were in the, no, here I save it. So this is the one. You see that it was just a second ago. I can open it. It will automatically recognize that it's a folder. And yeah, we are here done, and we have our regions visible. So both regions are located. So the long story short, we make a big tune from the raw EEG to the results that can be used in neural navigation system. And with this, I would like to finish here, and I'm open to answer any questions if they arise.
Wow, Mateusz, thank you so much. That was really a great tour through what's possible combining these software packages. And yeah, I feel quite impressed. And we are happy to answer any questions that would come from the audience.
Just a small comment. I know I was doing a few things very fast, and it might not be easy to follow this in a way that you would like to perform it by yourself, but definitely the recording of the session will be shared with you, so you can view it in slow-mo or whatever, and you are absolutely welcome to ask the questions, and we can join with the analysis with you for the very first round to help you doing this by yourself.
And can I ask some question?
Of course.
Okay. And thank you, Matthias. Thank you a lot for your presentation. And because I use BESA in my clinical work, I use BESA to do source localization for with high density EEG for my epilepsy patient, and it helps. So thank you so very much. But I also have some question. Actually, I have some wish, some hope for BESA. I hope I can solve problem this time, and I can project the dipole into BESA research in the MRI, and I can overlay several dipole together, so I can have a area of the epileptic focus.
Mm-hmm.
I really hope I can export. I can export the MRI with the dipole, with the multiple dipole in the DICOM format. And if I have that data, then I can give the date to the neurosurgeon, and we can do plan directly with the information from the EEG, high density EEG. So I hope to know, could I do that, and with what kind of software I can do that?
Okay, so that's a very easy answer I have for you. So first of all, you can do it right away with Mind. So with what I showed you, you can make the dipoles, numerous dipoles. And with this same approach, just the first part when I was exporting to Mind and creating the project, from there you can easily export it to DICOM already. However, the even better and cooler news is that, as you already mentioned, that you can overlay in this MRI, we have this upcoming feature that you will be able to export to DICOM directly from BESA MRI quite hopefully soon, because this is fully ready for almost a year or even more than a year. And we have it fully prepared, but we are stuck in the process of the medical device certification, not from our fault, but the authorized, so the authenticated body. They are filled with so many applications that we are just waiting in line. And we are hoping that will happen very soon, that we will be able to release. So
Okay.
that's two information I have for you.
Okay, thank you. How could I use the mind? I don't have this I think in the BESA research.
Yes, Harald?
Yes, it is an additional module that we sell on behalf of Clinical Neuroscience Projects, and that, as Matthias showed, directly works with BESA Research. So yeah, you can purchase this as an additional module if you like.
Okay, so I can connect with the I know you the person in China and
Yeah.
Yes.
to ask them.
Yes,
Okay,
absolutely.
okay,
Yeah, and of course, as Matthias said, we'll hope for clinical approval very soon of BESA MRI 4.0, which is the new updated version, and this will also be able to do this. But
but
yeah.
but at this moment, and we could not export the DICOM format MRI from the BESA MRI.
No, because we're
Yes.
waiting for clinical approval. Yeah.
Yeah,
And just to
and
note with Mind,
and
you will have the export, but also you have the option to load the other modalities. So I don't know if your practice includes the FLAIR, VBM, DTI, or whatever you do, like fMRI or SPECT, PET. Then all of these things can be used with Mind as well to overlay this together with BESA results. So that will be eventually beneficial for you to have a Mind if you do that. Yeah.
yeah, that would be great. And also, I found I cannot overlay the multiple dipole in BESA MRI at this moment.
No, you can.
I can.
Which version do you use?
I think it's 7. BESA 7.
Yeah, and MRI 3.0? That
MRI, I cannot remember.
I think that it's kind of the misunderstanding here because Kao, you, if I spell your name, say your name correctly, you would like to load multiple solutions, and that's not possible in the MRI. You just need to make in BESA Research the solution. You can in BESA Research you can append solution
Yeah.
and then save it as a one solution that contains all of this solution, and then you can load this to BESA MRI. That you can do.
Oh, okay.
So,
Oh,
so
okay.
there's
I
an
will try
option
it later.
there's an option in the source analysis save for BESA MRI in the file menu, and this will directly save it to the project that BESA MRI can then load it directly. Maybe Matthias, you can show it really
Okay,
quickly.
So
I
you
will
can
try.
see here you have this save solution for BESA MRI.
Okay, good.
You
Okay.
say that is saved here, and then if you go to BESA MRI,
Mm-hmm.
oh, why this happens?
So I can save several dipole together. You mean that?
Yes. But maybe if you have several separate solutions, you need to first combine them with append solution. Maybe if you write a quick message to our support portal, we can help you with more details.
Yeah.
Jean-Michel and Christian, welcome. And do you have any questions too?
Yes, thank you very much. It's very interesting. Yeah, I had a few technical points and a more major question. So the technical points is the handling of confidence intervals. Can you visualize confidence intervals of dipoles in this very nice 3D view? Like to see the relationship with the sEEG and the confidence dipole of the EEG.
So you can see it in BESA Research. We show the confidence interval. And you can see it in BESA MRI if you open Matthias just showed. I think, we're still missing that you can also visualize it in DENS and and Mind.
The question I had is, can you load any value? Because we compute epileptogenicity index on the sEEG in Marseille. It's our favorite tool. And can you visualize a set of value, load them equally as you did with the your values of a spike amplitude? It's just a vector. Can you load a vector of values that you've computed somewhere else incorporate it into this 3D view?
I think that would be possible because it's you can also load the CSV file instead of EDF. But for this particular technical question, before I give you the final answer, maybe we should have a separate call that I will just try it.
Okay. Yeah, it's just a way to trick, just to know the format, actually, if we know your file format.
Yeah, that's basically, if I can complete your question. So thanks for your nice presentation. So one of my questions was, there are different applications, and you save your results in some files. Is the data format is known? So it means that if we are doing something else, can we read some of the results from another software in your let's say BESA MRI or something?
Yes, so BESA MRI generates data in the VMR format. So this is Brain Voyager format. That can be easily open, for example, with NeuroElf or Brainstorm. They handle this format. So this is kind of not as familiar as Nifty, but still openable. And the results, like Clara results, can be open in Clara results are saved. So the distributed sources are saved in the Nifty format, following exactly the standard. So this should be straightforward. And the dipoles are saved in the text file because this is just the coordinates of the dipole.
Okay, great.
And the last question was about source localization in sEEG. Can you do it, or do you plan to do it?
We cannot do it yet, and actually, I think we talked about it briefly when I was over last year, and we'd be happy to work with you on something if that would be of interest. But currently, no.
Okay. Okay. Thank you so much. Hello to the others who I know, Pauli, Stefano.
Thank you. Yeah, and thank you very much for joining.
Good to meet Kao also. I mean, we're a growing community of sEEG, which is nice.
Thank you very much again.
Fantastic.
Thank you very much, and thank you very much for your questions.
Yes, thanks a lot. Thanks, Mateusz, again for presenting, and everybody for listening and contributing. And we'll pick it up again soon and hopefully improve even further.